if you have a curve defined by some function, f of x, and you draw the line tangent to that curve at some x value, that tangent line you draw is a very close approximation to the function f, at least for x values that are close to that place where you drew the tangent to. So we can actually use this idea. If you remember, we zoomed in on functions the first couple of days of school until they flattened out and looked like lines. Then we decided later that if we graphed the tangent line at that curve, at that place we were zooming in, and also the function, and we kept zooming out, then the tangent line and the actual function would seem like they became one. So very close to the point of tangency, a tangent line equation is a very close approximation of the function that you drew the tangent to. So we can use that to help us make approximations and solve problems and sometimes avoid complicated calculations. So check this out. So here on this slide there is a big formula in a yellow box. That formula is really just point slope form for the equation of a line with the y isolated. So you can kind of follow through this. I'm going to start with point slope form and show you where this formula comes from. Or if you prefer to just know that formula in the box, they're both ways to arrive at the linearization. This function, this tangent line equation, when we use it to make approximations, we call it the linearization of a function. So pick some x value that you want to draw the tangent line at. If it were the AP test, they would tell you exactly which x value to pick. And so we're going to need an x and a y to write the equation of a line. We're going to need a slope. So the x is the x value you care about. To find the y value, we're going to use that x value as the input to the original function that we have. So call it f of a. And we're going to need a slope. So there's a note on the top of your notes paper. We need to find the slope function, which is the derivative, and then evaluate it at the input value that we care about. In this case, that's the place where x equals a. So you can just see here all those words I just said. It means for x1 we're going to use a, for y1 we're going to use f of a, and for the slope we're going to use f prime of a. If I use those values, those expressions in the point slope form for the equation of a line, this is what I get. And if I want to think of it as a function though, I should isolate the y. So notice if I added f of a to both sides, then my f of a would be on the right hand side of the equal sign now. And this is a function that I can use. A is a known value. It's some number that we started with. We wouldn't be able to have started if we didn't know what a was. And the only variable in this equation is x. So this is a linear equation. It's a linear function of x. Some x value that I care about, I could use that as the input, and I would have my output as an approximation of the original f function at that place where whatever x value is I care to use. So I could give that function a name. We often give it the name L of x, L for linearization. So the linearization of f at a is simply the tangent line to f at a reorganized so that the y is by itself. If you need an approximation of the value, the output value of the function f, you can use it. Your f of x for some x that's pretty close to a is going to be approximately equal to L of x. Now notice L of x, the whole reason that we care to do this, you would study much more when you went on to things like differential equations and any computer programming that you might do afterward, is because it's really cheap. Whatever cheap means, it's really easy to perform the operations in a linear function. Multiply, add or subtract. Other functions can be really complicated. Sometimes you graph a function on your calculator and it takes forever to make that graph. That's not true when you type in the equation of a line, because lines, the operations you perform, are very easy for computers and most people to do. This is why we might want to use it. Let's see an example of how we could use it. All right, you're trapped on a desert island, and in order to get off, you need to know an approximation for the cosine of 1.75. And you don't have a calculator. You we're on this desert island without your calculator, and that's the only way that you know how to get the cosine of a number that's not, one of those spots on the unit circle. So using this idea of writing the tangent line to a curve and then using it to approximate other values on the curve, that's what we can use that to approximate cosine of 1.75, even though nobody knows cosine of 1.75 off the top of their head. So to do this, I'm using x equals pi over 2 as my a value. I'm going to need to figure out what my y value is. That's going to be f of pi over 2. I'm going to need to figure out f prime of x and use that to figure out f prime of pi over 2. So next slide. That's not this line. All right. So I know my a is pi over 2. F prime is negative sine of x. So my f prime of a is going to be the opposite of the sine of pi over 2. Sine of pi over 2 is 1. So negative sine of pi over 2 is negative 1. So this is my x, my m. I'm going to need to figure out my y. So my y is cosine of pi over 2. So f of a, cosine of pi over 2, which is going to be 0. Here we go. So I have conveniently provided this up here. If you didn't remember that, which is fine, I said you could just go back to point slope form for the equation of a line. We're going to have, I'll do it without even looking at that. This is going to be y minus, y1 we said was 0, equals the slope, which is negative 1 times x minus my x1 value, the x coordinate of my point that I know is pi over 2. That's pretty easy to add the 0 to both sides, and I'm going to get y equals negative 1 times x is negative x plus pi over 2. Okay, which is what we have over here if you'd use that formula. So what does this mean? This is definitely linear. L of x is negative x plus pi over 2, because pi over 2 is just a constant, and negative x, so that's a degree 1 equation. The only operations happening in it are adding, subtracting, multiplying. So I could use this now if I needed an approximation of cosine of 1.75. I want L of 1.75. And that's equal to the opposite of x, again, is 1.75 plus pi over 2. So I might have a really hard time simplifying that without my calculator, but if you put that in a calculator, you'd be shocked to find how close it is to the actual value of the cosine of 1.75. So you can see here, this is just that same thing, but written up nice and neat with typed out. Linearizations are pretty straightforward. They're only like a calculus topic because we need a derivative to figure out what to use for the slope. So they're not very complicated, but the most common error would be to try to tell me that answer you gave, negative 1.75 plus pi over 2, is equal to the cosine of 1.75. They're not equal. What you've given is an approximation. You just want to make sure that you're using an approximately equal to whatever function, in this case, you cared to find. Your linearization is supposed to be linear, so it's appropriate to use an equal sign there. But later, if you try to use that linearization to approximate some function value on your original function, you'd need to use an approximately equal to sign.